Hello, hello. Okay, so good evening, everyone. Good evening, sir. Uh, in today, I'm Josh, the presenter for this into the topic, which is the evolution of the CPU. So, so what does CPU? So what are so what is truly the CPU? Central Processing Unit or Central Processing Unit or the CPU is the brain of every computer, which is uh, which is in every computer in our modern world. It is it is CPU or the classical computing is one of the uh, cutting edge in our in terms of our technology, orchestrating instructions, managing data, and communicating with memory and peripherals. So CPU is really a one of the one of the one of the important components when it comes to shaping our technology into a advance at the same way in terms of like making a embedded systems, data centers, infrastructures, satellites, and anything related for the anything related for anything related for the technology which shape or modernize the hardware innovation of our systems, as well as the importance or the software architecture, which is or as well the software architecture of of the CPU, such as ARM 64, x86, with CV, and many more. Next slide. So this document explores the four critical aspects or key pillars of the CPU evolution. The first one is the mechanics of CPUs, the origin operating systems, the rise of x86 architecture, and the last one is the advancement in 32-bit processor pipelines and caches, which is maximizing efficiency and performance. So these four are the combination of how CPU modernized throughout the technology advancements. So let's go for the first one, which is the mechanics of the CPU, which is the core engine. CPU mechanics define its internal structures, how it processes instructions, and its interaction with memory and peripherals through a fetch decode execute cycle. The CPU operates as a sequential instructions processor, of, and that's what you call the fetch decode execute cycle is a sequential instructions. The core components, the central unit or CU, direct instructions and data flow. These direct instructions and data flow, these are what you call an assembly code, which is they are what you call what they call this just like in the programming, which is a just like in the programming language, which is a um variables. Um, the assembly could call this as a instructions, or those bits or those assigning in the addresses as a variable. They are what you call instructions. So arithmetic logic unit. These are one of the few importance for computing the for computing and stuff, performance of calculations and logical operations of each instructions of the peripherals or memory memory addressing and stuffs. And also, as I've mentioned, from the central unit, which is the instructions, this is in assembly. This is one of the things, just like a variable. When you create or assign a new value or an object, that's what you call in a low level in a low level word, or in a low level programming. That's what you call the registers. It's a fast temporary data storage. Then buses, these are the data pathways for the for communicating with communicating for communicating of communicating of bits, binary, and registers uh, through the CPU and to any peripherals and memories. So next slide. How the CPU mechanics evolution in action. In the early CPUs, which is in the 1970s, single cycle execution. We have a single cycle execution, limited parallelism, and then we only have a kilohertz and megahertz clock speed. Example for that is the Intel 4004 and 8008, using a single cycle execution only, where each instruction took several clock cycles with limited parallelism. And then in the modern CPUs, which is right now in 20s pipelining, we now have a more optimized pipelining, multi-core, which is have for which help us when it comes to uh, building building a building a low level and building a low level, or compiling a huge architecture of a huge architecture of architecture customization, such as x86, when it comes to dealing with low level peripherals and dealing with memories. We have now a branch prediction, caching caching for caching memory for billions of instructions per second. Uh, Example for this one is the Intel Core i9, and we also have the clock speed now, which is determine instructions execution rate. Early CPUs were in the, yeah, as I mentioned, kilohertz and megahertz ranges only. But now the the clock speed is now in the well, focusing on the gigahertz now for the clock speed. Also, I just wanted to overlap again the pipelining. It's a overlapping instructions stages to improve throughput. Then the multi-cores, these are what you call parallel execution, which is what you call multiple workers working independently. Then branch rotation, which this is what you call test branch for reducing the pipeline stalls. Cache memory, these are minimizes delays from slower main memory. So one of the examples of this one is the first one, first of the Intel, which is the 4004 in the 1971, which is a 4-bit CPU, single core, and simple ALU only, or simple ALU. Then the second one is the Intel 80386, or what you called in the 1885 or 1890s. In the 1890s is the I IG86. This is the first one, a 32-bit CPU, 4 gig memory addressing, and the first x86 to offer 32-bit architecture or ARCH. Also, just to be note, this uh, i386 is the one who made, or the first one to port the Linux, the first version of the Linux. And the last one is the AMD, or no, the third one is the Intel Core i9 2020 in the year 2020. It is now multi-core, multi-threaded, advanced advanced branch prediction from L1 to L3 caches. The last one is the AMD Ryzen Threadripper 9000 series in the 2025. This can be usable for making a server and stuffs, which is it has a 96 multi-cores, which is a lot for optimizing or compiling uh, a low level project. It has a 385 megabytes of L3 cache and 25% increase in AI or ML workloads. So, in summary for this one, understand the CPU mechanics explain why modern processors can execute billions of instructions per second, where areas early CPUs could barely handle thousands. So next slide. Let's proceed for the origin of operating systems. Origin of operating systems are always emerged to manage hardware resources and provide a platform for software, abstracting away manual hardware programming. Pro in the early computer days, they are required for manual programming of hardware, which is using a assembly, therefore was no abstraction layer. The early development, um, 1950s to 1960s, we have a batch processing, or oh, my mistakes. Assembly is a software programming, which is much more, which is in the modern days or in the early days in the 90s. It is one of the one of the technology or language which revolutionize our operating systems when it comes to talking to the hardware through the software. So let's proceed from the 1950s and 60s, such as the GMNNA IO, or input output handle sequences of jobs automatically. OS simplify repetitive tasks like input or output management and memory allocation. The key milestones for this one is in the 1969, which is the backbone or the parent of the modern OS, which is the Unix. This can be portable, multi-user, and multitasking in OS. And also, this one was made using C. And then in the 1981, which is the MS-DOS, simple OS for IBM PCs and x86 optimized. Then for the 1991, using the i386, this one is the rise of the Linux, which is an open source and Unix like kernel, or what you call GNU Linux. Then in 2004, uh, which was a parent of, or which was the child of Debian, which is Debian was a what you call this, ported the Linux into, or ported the kernel Linux into using it into for a modern operating system. Ubuntu is a user-friendly Linux distribution. And in the 2021, which is the Windows 11, the currently the currently version of the Windows right now is this have a modern GUI, improved security, Sir apologies. Uh, let's go for the Red Hat Red Hat Enterprise Linux, which is RHEL, or this can be used for the server. This can be used for the modern server, which is a commercial Linux distribution focused on the enterprise server security and long-term support. Then let's go for the Fedora 2003, cutting-edge Linux distribution and sponsored by Red Hat, used to test new technologies before enterprise adoption. Then we have now the Arch Linux lightweight rolling release Linux distribution designed for advanced users with full system control, which is it's your responsible for it's your responsible for customizing your own Arch Linux. Then we have now the Kali Linux in the 2013 security-focused Linux distribution used for penetration testing and digital forensics. And then we have now the Windows 11, which is the modern Windows system operating system, improved GUI, and better support for multitasking hybrid workouts. Then the last one in the Mac OS, in the world of Mac or Mac OS, the Sekia optimized for Apple Silicon, or this one used can be used from the M series of the silicon chip of the Apple. And also this one is Unix based, or what you call, they ported the Unix. As I mentioned before, Unix is the backbone of every operating system that what we have right now. It also feature improves productivity, performance, and seamless integration with other Apple device because of its architecture, which is an ARM64. And this ARM64 can be was made for was made or for was dedicated for our small devices, which is our tablet, cell phones, and stuff. And of CPUs always allow CPUs to multitask effectively, utilizing pipelining, interrupts, and multi-core CPUs efficiently. One of the examples of this one is the Intel 8086 CPU with MS-DOS enabled area personal computing, and modern CPUs with Linux leverages multi-threading, virtual memory, and advanced instruction sets. let's go for the top. Let's go for the third topic: the rise of x86 architecture. Intel's x86 family of CC processors. CC processors in 1978 dominate computing for decades due to its backward compatibility, versatility, and robust software system. Why it's backward compatibility? Um, New CPUs supported older software, and x86 is one of the uh, versatile when it comes to uh, versatile versatile architecture because this one this one is um, never gonna leave desktop laptop the desktop laptop world. Gonna be replaced since why is backward compatibility? When you are using a virtual machine and always talking to other architectures such as ARM64 CV for compiling or using their systems. x86 is uh, one of the best choices when it comes to porting other architecture. Just go for the evolution, which is let's just go for the modern x86, which is the Intel Core and AMD Ryzen, a multi-core 64-bit and single instructions, multi single instructions, multi instructions and stuff. The evolution of x86 processors. These are the evolution of x86 processors, as I mentioned. Then the last one, then the last one, 32-bit processor pipelines, caches. As CPU advances, 32-bit processors became standard, introducing pipelining caching to maximize efficiency. Pipeline, as I've mentioned before, pipeline divides instruction, execution into stages of sequence, such as fetch to decode to execute to memory to write back, allows multiple instructions to be processed simultaneously at different stages, increase instructions throughput without increasing clock speed, and also to maintain the overclocking or overheating of the CPU. Then what we have now, the caches. These are the small fast memory within the CPU to store frequently accessed data. We have levels for here. The first one is the L1, which is the fastest and smallest. The second one is L2, level 2, larger or slower. And the L3, the last one is the L3, the largest or shared. To store frequently accessed data, reducing latency from slower main memory. Impacts on performance for the 32-bit pipelines and cache drastically improve performance of 32-bit processors, allowing multitasking and multimedia applications. Enable modern software to run efficiently without requiring higher clock speeds. One of the examples of this one, let's go for proceed to the ARM Cortex M7 or this ARM Cortex or the ARM Cortex family. These are in our modern 32-bit is can be useful right now, can be useful for small embedded devices and using it for such as Raspberry Pi, Since right now in our system or in our laptop or desktop, we now use the x64-bit processor. So the 32-bit in the modern world, or in our current technology, we use it for small devices. One of the examples for using it in ARM Cortex ESP32 with CV and the microchip PIC32MS. Solution: the symphony of innovation. The evolution of CPUs is a testament to continuous innovation across hardware and software, leading to today's powerful computing capabilities. As I mentioned, um, CPU mechanics. In summary, just to summary, the CPU mechanics foundation for instruction processing, the operating system allowed CPUs to manage tasks efficiently, pipelines and caches, maximize efficiency and performance, and the x86 architecture standardized CPU design and assured software compatibility. Together, these elements explain why today's processors are orders of magnitude more powerful than early machines while maintaining backward compatibility, supporting complex software ecosystems. So that's all. Thank you for listening, and thank you for listening. And I now conclude my presentation, or this presentation. As in, thank you for listening and have a great day. Hello, hello.